Welcome back to another session. In this session, we are going to understand what is stress. What is exact meaning of stress? Right? So to understand exact meaning of stress, I should take some 6-7 special cases. From the 6-7 cases, you can easily understand what is real meaning of stress. Right? Okay. I am taking first case here, right? First case. A uniform cylindrical rod is there. A uniform cylindrical rod is there. Length of this rod is 1000 millimeters. Area of cross section of this rod is 10 millimeters square. Here A means area of cross section. Mass of this rod is 10 kg. And Young's modulus of this rod is 70 GPa. And this bar is carrying a force of 10 newtons. A force of 10 newtons. See this diagram, man. Observe this diagram. First you copy. You copy and observe. Here I have drawn a bar. Length of this bar is 1000 millimeters. 1000 millimeters. Area of cross section of bar is 10 millimeters square. Mass of this bar is 10 kg. And this bar is carrying an axial load of 10 newtons. An axial load of 10 newtons. Okay. During my B.Tech, I attended one campus interview. In that campus interview, the interviewer asked me this question. At the beginning itself, man, right? I introduced myself. Then that fellow asked this question. He has drawn a bar like this. And he asked me a question, a simple question. Dear Lakshman, what is stress in this bar? He has drawn this bar and he asked, what is stress in this bar? In those days, I told like this. Stress is equal to force by area. Force is 10 newtons. Area is also 10. And I told it is 1 newton per millimeter square. Without any hesitation, I told stress carried by this bar is 1 newton per millimeter square. Many of you may think like me, is it not? If I ask you same question, most of you may reply, the stress carried by this bar is 1 newton per millimeter square. Because we believe stress is equal to force by area. Right? We believe stress is equal to force by area. Oh, force is 10 newtons. Area is 10 millimeter square. So 10 by 10, 1 newton per millimeter square. Like that we think. But what is actual stress in this bar? This bar will carry any stress or this bar will not carry stress. Definitely this is wrong. Now, whatever I told in that interview, it was wrong. It is not 1 newton per millimeter square. Then how much? Then how much? The answer is stress carried by this bar is equal to 0. Stress carried by this bar is equal to 0. Why stress carried by bar is equal to 0? Stress is not applied force by area. Stress is resisting force offered by body by effective area. What is resisting force offered by this bar? Is this bar offering any resisting force to external load? This bar is not offering any resisting force. This bar will not be in static equilibrium because only rightward force is acting. There is no balancing force here. There is no opposite force to this 10 newton force. This bar cannot be in static equilibrium. This bar tends to move towards right with sudden acceleration. Since resisting force offered by this bar is 0, Stress also 0, man. Right? So stress is equal to resisting force by area. In this problem, resisting force is 0, stress also will be 0. So don't think, never define stress is equal to force by area. Don't say like that, man. Stress is equal to resisting force by area. Resisting force by area. In this example, the bar is not offering any resisting force. You are applying 10 newtons force. Bar is not resisting. Simply bar will follow 10 newtons force. This bar tends to move towards right with certain acceleration. Right? So what is acceleration? From Newton's second law, F is equal to mass into acceleration. Here what is resultant force carried by this bar? Resultant force is 10 newtons and the mass is 10 kg into acceleration. Then what is acceleration? 10 by 10. That means 1 meter per second square. This bar moves in the direction of force with an acceleration of 1 meter per second square, because this bar is not in equilibrium, man. Only one force is acting. Towards left, no other force is acting. No balancing force is acting. So simply this bar moves towards right. Understand, man? So stress carried by this bar is 0. What is acceleration of this bar? 1 meter per second square. 1 meter per second square. Now one more question, man. What is deformation in this bar? Will this bar deform or will not deform? This bar will not deform because there is no opposite force. Only one force is there. You take here one bar is there. I am applying 10 Newton force. Simply, this bar is moving towards right. So deformation is 0, strain is 0, stress is 0, strain energy stored by this bar also will be 0. Okay? Only acceleration will be there. Maybe after some time, some displacement will be there, velocity will be there, acceleration will be there. So this problem is not SYM problem. This problem is what problem? Engineering mechanics problem. This is not SYM problem, man. This is engineering mechanics problem. Okay? Now, clearly you write like this, man, right? So, you might have copied this bar. You might have copied this bar. Then write in this fashion. Write in this fashion. So, number 1, stress. Stress is equal to 0. Number 2, deformation. Deformation is also 0. Number 3, strain. Strain is also 0. Number 4, strain energy. Strain energy. Since it is not deforming, this bar will not store any energy. Strain energy is 0. Then acceleration. Definitely acceleration will be there. Acceleration of this bar is 1 meter per second square. Maybe after some time, this bar may carry kinetic energy, not strain energy, man. Understand? This is very popular question. In many interviews, the interviewer would try to ask this kind of question, especially when student says, my strongest subject is SOM, my interesting subject is SOM, I like SOM. If you say like this, definitely they will ask you this question. A bar will be given like this with some load, and simply they will ask you, what is stress in this? What is strain in this? What is strain energy? What is deformation in this? All these things they will ask. So all those things are 0 except acceleration. Understand, man? All those things are true, are zeros except acceleration. So in this case, what you have learned, man? In this case, what you have learned? Stress is not applied force by area. Stress is resisting force by area. Okay? Right. This is first case. Then I am taking second case. Let us move to second case. But before that, you write clearly like this, man. All these 5, you write. So clearly write all these things. Okay. Let us move to second case. Let us move to second case. In second case, again I am taking a cylindrical bar. This bar is carrying loads like this. Towards right, a force of 10 newtons is acting. Towards left, a force of 5 newtons is acting. Again I will ask you same question, man. What is deformation of this bar, strain in this bar, stress in this bar, acceleration of this bar? All these things we have to find again. You know, if you observe this, towards right 10 Newton force is acting, towards left 5 Newton's force is acting. Obviously, this bar cannot be in static equilibrium. What is the resultant force, man? Resultant force is 10 minus 5, 5 Newtons. So this bar will not be in static equilibrium. Then tell me how much stress will act. How much stress will act in this bar? Again stress will be 0 or some stress will be there. Again it will be 0 or this bar is carrying any stress. Think about it. In most of the gate problems, always bars will be given, right, with balanced loading. If loads are not balanced like this, what to do? How to do? So these things we are going to learn. What is stress in this bar? Is it 0 or something? Or something? If it is something, what is that something? Right? Let us try to do it, man. So first I am saying this bar will carry stress. No doubt, man. This bar will carry stress. Right? How? Like this. Divide this problem into two different problems. Divide this problem into two different problems. In first problem, 5 newtons rightward, 5 newtons leftward, and in second problem, 5 newtons rightward and 0 newtons leftward. 5 plus 0, 5. 5 plus 5, 10. In SOM, we can divide a given problem into number of simple problems. Or reverse also we can do. We can combine number of simple problems into a single big problem. So here what I am doing, man, I divided this problem into two problems. In first problem, both ends 5 are acting. In second problem, only this 5 is acting. So this kind of thing is called principle of superposition. In SOM, we can definitely use principle of superposition. Why? Because in SOM, we deal small deformations only. Wherever you use small deformations, there you can use principle of superposition like this. Observe first problem, man. You forgot about second problem. Observe first problem. What is stress in this bar? What is stress in this bar? See, definitely this bar will be in equilibrium. You forget about second problem, man, right? Try to concentrate only on this problem. Okay? Right. This bar will be definitely in static equilibrium. If this entire bar is in static equilibrium, every point of bar also will be in static equilibrium. If the entire structure is in equilibrium, every point of structure also will be in static equilibrium. Now, I consider static equilibrium of this point. If the entire bar is in equilibrium, this point also will be in equilibrium. Let us consider equilibrium of this point. This point is carrying an external load of 5 newtons. This point is carrying an external load of 5 newtons. Unless it is balanced by an equivalent opposite force, this bar cannot be in equilibrium. But we know this is in equilibrium. That means there shall be an equivalent opposite force. There shall be an equivalent opposite force This is action. I am applying this. This is reaction from bar. This is resistance offered by bar material. This is active force. This is resisting force. Similarly, you can take equilibrium of this point. A rightward force of 5 newtons is acting. There should be an equal and opposite force to balance this 5 Newton force. Who is generating this? I am applying this. Who is generating this? Material of the bar itself. So material of the bar itself is generating an equal and opposite force. So tell me, man, what is resisting force offered by bar here? Applied force is 5, resisting force also 5. Stress is equal to resisting force by area. So sigma is equal to resisting force is 5, area of cross section is 10, 5 by 10 is 0.5 Newton per millimeter square. So this bar carries stress. This bar carries stress. That stress is 0.5 Newton per millimeter square. Second, let us try to find deformation. Deformation delta is equal to PL by AE. Deformation in bar is given by PL by AE. Here what is P? Is it resisting force or applied force? Resisting force. That means 5 into what is length of the bar? 1000. What is area of cross section? 10. What is Young's modulus? 70 GPa. 70 GPa means 70 into 10 power 3. Okay. So deformation is also there. How much deformation? You may calculate this deformation, man, right? So this is delta. Then what is strain in this bar? Strain is equal to deformation by original length. So delta by L is again 1000. So this bar is carrying stress. This bar is undergoing deformation. This bar is straining also. And strain energy stored by bar is given by half into P into delta, right? So even this bar may carry strain energy also. You know, all this formula I will derive shortly. Okay, for the time being, you may copy. So even strain energy also will be there in this bar. But you know, from second problem, okay, from first problem, we are getting all these things, man. If you observe second problem, this bar will be in equilibrium? Definitely no. This bar tends to move towards right. With how much acceleration? Like this. So the acceleration of this bar is equal to force by mass 5 by 10. That means 0.5 meter per second square. So combine all the results, man. This bar is not in equilibrium. Come back to original bar. This bar is not in equilibrium. This bar is moving with an acceleration of 0.5 meter per second square. But at the same time, this bar carries stress. This bar carries strain, deformation, strain energy, etc., etc. Many students may think like this, man. Only static structures carry stress. It is not like that, man. Any structure may carry stress. Even moving elements also carry stress. Static structures may carry stress. Moving elements also may carry stress. Whenever structure offers some resistance to external load, definitely stress will come. Understand, man? So this is our second case. I should say this problem is combination of SOM and engineering mechanics. This kind of problem never came in GATE exam. This kind of problem never came in GATE exam. In all GATE papers, you know, always forces would be balanced. Left side fair, right side fair. Left side 10, right side 10. Like that they are giving, man. But in future, definitely, they may try this kind of problems, man. Because the trend is like this, man. In GATE papers, you know, in recent GATE papers, you know, they are trying to combine different subjects. In same problem, they are trying to combine different subjects. So this problem is combination of SOM and engineering mechanics. This is the problem of SOM. This is the problem of engineering mechanics. Be careful, man. And in coming sessions, we are going to do some complicated problems like this, man, right? So here only left side 5, right side 10. You can easily understand. But you know, in coming problems here, one section will be there. Here, one section will be there. Maybe here 6, here 10, like that, man, right? So we are going to do those kind of problems also in coming sessions. So this is my second case. Let's move to third case, man. Have you copied? Please copy. Please copy all these things. Please copy all these things. I hope you copied all these things. Let us move to next case. Let us move to next case. Again, the third case. So I am drawing a uniform cylindrical bar. A uniform cylindrical bar. Uniform cylindrical bar. This bar is carrying an axial tensile force of 10 newtons on both ends, man. That means this bar will be in definitely equilibrium. The original cross-sectional area, right? I may refer this as A naught, man, right? A naught means original cross-sectional area. This is 10 millimeter square. Original cross-sectional area is 10 millimeter square. When you apply this tensile force 10 newtons, definitely length of this bar will increase. When length increases, what will happen to cross-section? When length increases, area of cross-section will decrease. So, after application of 10 newtons force, area of cross-section has become maybe 9.5 millimeter square. Listen carefully, man. Before application of this load, area of cross-section is 10 millimeter square. When you apply this load, area of cross-section is decreased to 9.5 millimeter square. When you apply tensile force, length will increase, area will decrease. Understand, man? Before load, area of rod is 10 millimeter square. After application of load, since length is increasing, area is 9.5 millimeter square. Now I would like to ask you one question, one simple question, man. What is stress in this bar? What is stress in this bar? Is it 10 by 10 or 10 by 9.5? A simple question, man, right? Is it 10 by 10? Force is 10. Original area is 10. Is it 10 by 10 or 10 by 9.5? Which is correct? 10 by 10 or 10 by 9.5? I am sure in your BTech, you might have found stress like the stress in this bar is equal to 10 by 10. That means 1 Newton for, you might have found stress in this fashion only, man. You never find stress with respect to the area after loading. 10 is area before loading and 9.5 is after loading. So are you using before loading area or after loading area? So in our BTech definitely you might have used area of cross section of bar before loading. So 10 by 10 1 Newton per millimeter square. Most of you may answer like this. And some of you may say stress is equal to 10 by 9.5. Which is correct, man? Which is correct? 10 by 10 is correct. 10 by 9.5 is correct. Which is correct? 10 by 10 is correct or 10 by 9.5 is correct? Which is correct? Some of you may think it is correct. Some of you may think it is correct. I am saying both of you are correct. Both are correct, man. Both are stresses. But there are two stresses here, right? First is engineering stress. Engineering stress. If you calculate stress on the basis of original area of cross section, area of bar before loading. If you use original area of cross section, that stress is called engineering stress. But what is actual stress? The actual stress or true stress? The actual stress or true stress, man? The actual stress or true stress is equal to the actual force by the actual area of cross section. So here this is 10 by 10. Engineering stress is 10 by 10. The actual stress or true stress is P by actual area, that means 10 by 9.5. Understand, man? Don't confuse. If you use original area, that stress is called engineering stress. If you use actual area, that is called actual stress or true stress. Understand? What stress you found in BTech? Most of the times we find engineering stress only, man. All of our calculations, either design or non-design things, every stress we are calculating by using original area of cross section. That means we are finding engineering stress, man. We are not finding the actual stress. Be careful, it is another important question, especially in interviews they will try to ask this kind of, even in gate exam also they can ask, they may give you a bar like this. Simply they may ask you, what is true stress and what is engineering stress? Engineering stress is equal to 10 by 10, true stress is equal to 10 by the actual area of cross section after loading. Clear, man? What is engineering stress and what is actual stress? Okay? Right. Please copy. Please copy all these things. So I hope you copied this. Now you understood what is the meaning of engineering stress and what is the meaning of actual stress. Let us take one more case, man, right? Fourth case. A bar is there and this bar is made with three different materials, man. Maybe this is P, This is also pre. First section is made with aluminium. Second section is made with copper. And third section is made with steel. So first section is made with aluminium. Second section is made with copper. Third section is made with steel. Okay. And length of each section is same. Length of each section is same. Every section carries a length of L. And clearly they have given Young's modulus of aluminium is less than Young's modulus of copper. Young's modulus of copper is less than Young's modulus of steel. Like this, they have given. It is previous gate question. Wonderful question. Conceptual question. So they have given like this, man. And what is question? Question is like this. What section carries highest stress? Is it aluminium section or copper section or steel section? Which section carries highest stress? Which section carries highest stress? What section? Somebody may think aluminium. Somebody may think copper because it is middle section. Many students may think middle cross section may carry highest stress. And somebody may think steel may carry highest stress. Steel may carry highest stress. What section carries highest stress? Listen now. I am taking one bar here, right? One bar like this. This bar is carrying an axial force of P and area of cross section is A. Original area of cross section. And this bar is made with wood. Wooden bar, man, right? What is stress in this bar? Stress means engineering stress, man. If nothing is mentioned, stress means what? Engineering stress. Engineering stress is equal to P by A. Engineering stress is equal to P by A. Understand? You copy this, man. First you copy this, then copy this, because a little more explanation is there. You copy this original case and this case also. So currently we are dealing fourth case. So first you may copy this diagram, then you draw this diagram. So a wooden bar is taken. That wooden bar is carrying an axial tensile force of P. Area of cross section is A. So sigma is equal to P by A. Sigma is equal to P by A. Like that you can understand. I hope you copied, man, right? Okay. Now, this is not wooden bar. For instance, this is not wooden bar. Maybe this is steel bar. What is stress in this steel bar? Again P by A or something different, man. Wood is different, steel is different. Their properties are different. But what is stress here? What is stress here? Again P by A. Now this is not steel bar, man. Maybe this is copper bar. What is stress? Again P by A. Now it is not copper bar. It is aluminium bar. What is stress in this bar? Again P by A. What is your understanding? What is your understanding? Stress is independent of material. Stress is independent of material. Stress is equal to resisting force by area, man. It is not function of material. Please write it, man. Write this important sentence. Stress is independent of material. Stress is independent of material. Stress is independent of material. Only thermal stress is function of material, man. Ordinary stress is not function of material. The bar may be made with wood or steel or copper or aluminium. When force is same, area is same, you will get same stress. Now you answer this question. Area of cross section of every section is same and every section is carrying same force. What is stress in every section? Stress in aluminium, P by A. Stress in copper, P by A. Stress in steel, P by A. That means what? All sections will carry same stress. Understand, man? Please write it. In above bar, all sections carry same stress. In above bar, all sections carry same stress. All sections carry same stress. Okay? Somebody may do mistake here, man, right? You know, many students tends to use Hooke's law. Hooke's law says something like this. Hooke's law says stress is equal to Young's modulus into epsilon. Stress by strain is Young's modulus. Stress is equal to Young's modulus into strain. Some students may tend to use this, man. They think like this. Since Young's modulus of steel is highest, stress will be highest in steel. They claim like that. Since E is highest for steel, the stress carried by steel is highest. Is it so, man? Is it so? Definitely not. Of course, Young's modulus for steel is more. But what is strain? What is strain? In what section strain will be lowest? Wherever E is more, there strain will be low. You know, strain is equal to sigma by E. Wherever Young's modulus is more, there you will get low strain, man. So E is more for steel, but epsilon is lowest for steel. So this product is constant, man. Product of E into epsilon is constant for all these three sections, man. All these three sections. More the Young's modulus, less the strain. Product is same. So don't do mistake, man, right? So in this example, all sections will carry same stress. Understand, man? Right. Now, I would like to ask you one more question, man, right? What section undergoes highest deformation? What section undergoes highest deformation? Yeah, deformation is also same. Deformation is also same in all these sections, man. Deformation also same. Stress is same. Deformation is same. Let us see. Deformation in aluminium section is equal to P into L by A into E aluminium. Deformation in copper is equal to P into L by A into E copper. Deformation in steel is equal to P into L by A into E steel. Now you can easily tell me which section undergoes highest deformation. Wherever, you know, PL is same, A is also same, only variable is E. This E is in denominator, right? This E is in denominator, right? That means what? In what section you may expect highest deformation, man? Since Young's modulus of aluminium is lowest, delta aluminium will be highest. Wherever E is highest, there delta will be lowest, man. Understand? So what is your answer? Which section carries highest deformation? The answer is aluminium section. Don't say all sections carry same deformation. Stress is same, man. Stress is independent of material, but not strain. Strain is very much function of material. Understand, man? Right, right. Aluminium section carries highest deformation. Aluminium section carries highest deformation and highest strain. Strain is equal to deformation by length. Length of every section is same. Since deformation in aluminum section is highest, strain also will be highest, man. So aluminum section carries highest deformation and highest strain. So stress is same in all the three sections but not strain. So please write this sentence also, man. Strain is function of material. Strain is function of material. Strain is function of material. Stress is not function of material, but strain is function of material. Strain is function of material. Wonderful. So if you want to copy these things, man, right? Delta aluminum is equal to PL by A into E into AL. Like that, delta copper and delta steel. Deformation in aluminum, deformation in copper, deformation in steel. So copy this, and from these three we can easily understand aluminum section may carry highest deformation and highest strain. Okay, man? Let me go to next case, man, right? Let me go to next case. Let me go to next case. In next case, a cylindrical bar I am taking. What cylindrical bar? A rigid cylindrical bar. A rigid cylindrical bar. It is carrying an axial tensile load of P and area of cross section is A. And what kind of bar it is, man? I am clearly saying it is a rigid bar. A rigid bar is carrying an axial tensile force of P. Length of the bar is L. Two questions, man. First question. What is stress in this rigid bar and what is strain in this rigid bar? What is stress? What is strain? What is stress? What is strain? So obviously you may know what is strain. So what is strain in this rigid bar? What is deformation in this rigid bar? Since it is rigid bar, it cannot deform. Delta will be 0. If delta is 0, what is strain? Strain is equal to delta by L. Since deformation is 0, strain also will be 0. Strain in this bar is 0. But what about stress? Stress is also 0. Stress is also 0. You know, this bar will be in equilibrium. If this bar is in equilibrium, so about this point, a resisting force of P will develop. About this point, a resisting force of P will develop. So here resisting force is P, area of cross section is A. So stress is 0 or stress is available. So stress is equal to P by A. So don't think, man, rigid bar carries 0 deformation, 0 strain. It doesn't mean stress also 0. Be careful, man, in this example, stress is available, but not strain. Strain is 0, but stress is available. So be careful. Sometimes stress may be available, strain may not be there. Sometimes strain may be there, stress will not be there. We are going to see all these things in coming sessions, man. Already we have seen this case. In coming sessions, somewhere strain will present, but stress may be 0. Right? So don't think if stress is 0, strain is also 0. If strain is 0, stress is also 0. Not like that, man. Sometimes stress could be 0, strain may present. Sometimes strain may be 0, stress may present. Understand? Don't confuse, man. Understand? Right. Please copy. Okay, let me go to another case, man, right? Let me go to another case. This is my sixth case. This is my sixth case. In this case, again I am taking a bar element, a uniform cylindrical bar I am taking here, right? And this bar is carrying an axial tensile force of, this bar is carrying an axial tensile force of maybe 100 kilonewtons. This side also 100 kilonewtons. And area of cross section, even I give area of cross section also, right? So area of cross section A is equal to 10 millimeter square, and ultimate point stress of this bar is 100 Newton per millimeter square. All of you copy this. So another point we are going to learn here, another important point we are going to learn here, right? So here I have taken a uniform cylindrical bar. Area of cross section of this bar is 10 millimeter square, and this bar is carrying 100 kilonewtons, and ultimate point of this bar is 100 Newton per millimeter square. Okay, what is question then? What you have to find in this bar? Tell me. What is maximum possible stress in the bar equal to what? What is maximum possible stress in this bar? What is stress? What is maximum stress in this bar? Is it 100 into 10 power 3? 100 kilonewtons means 100 into 10 power 3 by area is 10. That means 10,000 Newton per millimeter square. If you use force by area formula, the stress will come out as like this: 10,000 Newton per millimeter square. Right? But what is ultimate point stress? 100 Newton per millimeter square. Now answer my question. What is maximum possible stress in this bar? Is it 100 Newton per millimeter square or 10,000 Newton per millimeter square? What is your answer, man? Is it 100 or 10,000? The answer is obviously 100 Newton per millimeter square. What is ultimate point? Maximum possible stress without failure is called ultimate point. If stress is more than ultimate point, simply structure will break. This bar cannot carry this much of stress, man. When stress reaches 100, this bar will break into two pieces. So, if they give this bar and if they ask you, what is maximum possible stress in this bar? You have to say ultimate point. No structure carries stress more than ultimate point. Only up to ultimate point, the stress will present. Beyond ultimate point, the structure will break into pieces, man. Understand? And again I am saying, man, in SOM, we are using gradually apply load. All of a sudden you don't apply this load. Gradually you will apply load. First 0, 1, 2, 3, 4, 5, 10 newtons, 13, 14, 16, 100, 1000, like that, man. When a particular load reaches, this bar will break into two parts. This bar cannot carry this load. Theoretically, they may put 100 kilonewtons, but it cannot carry this load. When stress reaches ultimate point, simply this will fail. Understand? Right. So write down one point here. Maximum possible stress in any structure, maximum possible stress in any structure is ultimate point stress. Ultimate point stress. Okay? Right. Let us come to last case, man. Again a bar I have taken. This bar is carrying an axial force of P, but here P is suddenly applied load. P is suddenly applied load. So the stress is equal to, stress may be P by A when P is gradually applied load. When load is suddenly applied, stress also will be double. So if this load is sudden load, stress will not be P by A, man. Stress will be 2P by A. That is why sudden loads are dangerous loads, man. As compared to gradually applied load, sudden loads are always dangerous. Sudden load induces double the stress. Okay? So you have to understand like this. When load is gradually applied, stress may be P by A, but when load is suddenly applied, stress will be 2P by A. It's not P by A. There is one derivation behind it. Blindly I am not saying, man, right? In coming sessions they may learn it. Okay? So in this session, I tried to explain various aspects of stress. Or many students may have some blind spots on stress. Now, I hope all of your confusion, all of your doubts might be vanished in terms of stress, with respect to stress. In coming session, I will define stress, man. Still I didn't define stress. In coming session, I will define stress. Then I will classify stresses. And I will define every stress. Then I may define strain. I classify strains. I will try to relate stress and strain. In this sequence, we are going to move in coming sessions. I hope you enjoyed this session, right? So until next session, good day, good luck. Thank you.